Hi everyone, my name is Winona Thatcher and this is Teaching About Neurons. So let's get started. We're going to start with the synapse. So we're going to talk about the presynaptic membrane, the postsynaptic membrane, synaptic vessels, and storage granules. First of all, over to the right is a nice visual of the synapse and the presynaptic membrane, which is right here. So how that works is the presynaptic neurons send signals which go through the presynaptic terminal or membrane. Action potential races along the axon, activating sodium and potassium channels, and lands in the presynaptic terminal. This activates the voltage-gated calcium channels to open and release calcium into the cytoplasm. Postsynaptic membrane. So we're looking right here. This works in a way that the postsynaptic neuron accepts the neurotransmitters in its receptor region, which is on the dendrite or the cell body. Neurotransmitters bind to the receptor sites on the postsynaptic neuron. Simply, the presynaptic neuron delivers and the postsynaptic neuron receives. Synaptic vesicles. These are going to be right here, these little pink things. These little dots in here are the neurotransmitters, and the pink things are the vesicles. So the presynaptic terminal stores high concentrations of neurotransmitter molecules in these vesicles, which are tiny, nearly spherical packets. Storage granules store the nutrients that the cell needs for growth and survival. Now, steps of synaptic transmission. Action potentials. Step 1 is action potentials travel down the axon. At the presynaptic terminal, the depolarization enables calcium to enter the cell. 2. The release molecules diffuse across the narrow cleft, attach to receptors, and alter the activity of the postsynaptic neuron in any of several ways. 3. The neurotransmitter molecules separate from their receptors. Step 4. The neurotransmitter molecules may be taken back into the presynaptic neuron for recycling, or they may diffuse away. 5. Some postsynaptic cells send reverse messages to control the further release of neurotransmitter by presynaptic cells. Now, what major role do calcium ions play here? So I have this little calcium ion right here. Calcium releases the neurotransmitters from the terminals and into the synaptic cleft, the space between the presynaptic and postsynaptic neurons. Release zone. What is the release zone? The release zone is the region of a presynaptic axon terminal, where synaptic vessels discharge neurotransmitters molecules into the synaptic cleft. What happens to the neurotransmitters here? They are released into the synaptic cleft. So here's some questions. What happens to the neurotransmitters during inactivation? Neurotransmitters are released into the synaptic cleft once in the synapse. They must be taken out or chemically inactivated in order to prevent constant stimulation of the postsynaptic cell and excessive firing of action potentials. They are either inactivated or taken into reuptake. Now, what's reuptake? Neurotransmitters are reabsorbed by the sending neuron. Proteins quickly move the molecule back into the presynaptic cell. Reuptake serves two purposes. One is recycling, and 2 is halting the effects of the postsynaptic cell. What is enzymatic deactivation? This is a mechanism that makes neurotransmitters inactive and occurs when an enzyme changes the structure of a neurotransmitter so that it can no longer be recognized by the receptor. And here is a little example on the left of reuptake with serotonin. Okay, excitation versus inhibition. So excitation refers to depolarizations, makes the inside more positive. Inhibition refers to hyperpolarization and makes the inside more negative. Now, how do excitatory versus inhibitory neurotransmitters affect the next neurons? PSP versus IPSP. Excitatory neurotransmitters affect the next neuron or neurons by having graded potentials that push the neuron closer to the threshold and make an action potential more likely. Inhibitory neurotransmitters affect the next neurons by having greater potentials that push the neuron further from the threshold and make an action potential harder to achieve. So excitatory makes the action potential more likely, and inhibitory makes the action potential harder to achieve. Excitatory neurotransmitters result from sodium ions entering the neuron, and inhibitory result from the flow of negatively charged chloride ions into the cell. Now, action potential depends on the sum of excitations and inhibitions in that area. Temporal and spatial summation. If you look to the right, we have a little example here of what that might look like. So temporal summation is repeated stimuli within a brief time combine their effects. This is called temporal summation, or summation over time. Spatial summation is a property of synapses, and it means summation over space. So temporal is time, spatial is space. How are they related to EPSPs and IPSPs, and how can they affect the electrical charge and potential of an action potential in the next neuron or neurons? Temporal summation. When two EPSPs are produced within a short time, the second EPSP is added to what is left of the first one, creating temporal summation. EPSPs add up and arrive one after the other. Spatial summation. Action potential reaches on several presynaptic neurons, arrive at the postsynaptic neurons simultaneously to result in EPSP, arriving all together, creating a spatial summation. Temporal summation and spatial summation occur together when a neuron receives input from several axons in succession. And that is going to be it for my presentation. I hope that it was helpful, and I hope y'all enjoyed it. Have a great rest of the semester, and thank you so much for listening. Okay.